You think you understand black holes. You don't. You've heard the words event horizon, singularity, space-time curvature. But here's what nobody tells you. We don't actually know what happens inside them. And that's not because we need better telescopes. It's because our two best theories of reality are having a screaming match, and the black hole is where they meet to fight. Most people picture a black hole as a cosmic vacuum cleaner, a giant space monster that sucks everything in. Scientists talk about singularities and information paradoxes, like these are explanations. That's not an answer. That's a label. You didn't explain what a black hole does to information. You gave it a fancy name and hoped nobody would notice. Let me show you what I mean. Take a book, any book, burn it. The information isn't gone, it's just scrambled. Every ash particle, every photon of light from the fire carries a piece of the original pattern. In principle, if you could collect every bit of smoke and heat, you could run the physics backwards and reconstruct the book perfectly. That's how the universe works. Information is conserved. Nothing truly disappears. Now, throw that same book into a black hole. According to our equations, the book hits the singularity, and what? Does the information vanish forever? Does the universe forget what that book was? If so, then everything we know about physics is wrong. But wait, here's where it gets weird. Stephen Hawking showed us that black holes aren't perfectly black. They glow. They emit radiation and slowly evaporate. So maybe the information comes back out in that glow. Problem solved, right? Wrong. The radiation looks completely random. It's like trying to reconstruct the book from the pattern of sparks flying off the fire. It seems impossible. This is where most explanations cheat. They wave their hands and say, it's all very mysterious, or quantum mechanics solves everything. Those aren't explanations. Let me show you what we actually know, not what we guess. A black hole isn't a thing. It's a region of space-time where gravity has bent the fabric of reality so severely that escape becomes impossible. Think of it like this. Imagine you're in a river flowing toward a waterfall. Far upstream, you can paddle against the current. You can escape, but there's a line, let's call it the point of no return, where the water flows faster than you can paddle. Cross that line, and you're going over the falls no matter what you do. The event horizon is that line. But instead of water flowing, it's space-time itself falling into the black hole. At the horizon, space falls inward at the speed of light. Since nothing can travel faster than light, nothing can swim upstream. You're stuck. Now here's the first weird part. From your perspective, falling in, nothing special happens at the horizon. You don't hit a wall. You don't feel anything different. You just keep falling. The horizon isn't a physical surface. It's more like the point where yesterday becomes unreachable. You can't go back to yesterday. And once you cross the horizon, you can't go back to the outside universe. But from the outside, watching you fall, something very strange occurs. As you approach the horizon, time dilation kicks in. Your watch appears to slow down. Your movements get sluggish. As you reach the horizon, you appear to freeze, your image getting redder and fainter until it fades away. To the outside observer, you never actually cross the horizon. You just fade away, frozen at the edge forever. This creates our first puzzle. Which perspective is right? Are you frozen at the edge, or did you fall through? The answer depends on who's asking. Both perspectives are equally valid. This isn't a flaw in our understanding. It's a feature of how space-time works. But that's just what we see from outside. What about the information you carry? Your memories, your DNA, the pattern of atoms that make you. Where does that go? Let's be more precise about what we mean by information. When I say you carry information, I don't mean you have a library card in your pocket. I mean that the arrangement of atoms in your body represents a specific pattern, a pattern that took billions of years of evolution and decades of experience to create. Every scar, every memory encoded in neural connections, every unique isotope ratio in your bones. That's information, and physics says it can't just vanish. Here's a concrete example. Take a simple hydrogen atom falling into a black hole. That atom carries information, which energy state it's in, how it's spinning, how it's correlated with other particles it interacted with before falling in. These quantum properties are as real as the atom's mass or charge. Where do they go? Here's where our two best theories start throwing punches at each other. General relativity. Einstein's theory of gravity says you fall right through the horizon toward the singularity. All your information gets crushed into that point of infinite density where the math breaks down. Information gone. End of story. But quantum mechanics says, hold on. Information can't just disappear. That's against the rules. The quantum world demands that information be conserved, no matter what. If you put information into a system, it has to come out somewhere, somehow. Watch what happens when we stop guessing and start measuring. When Hawking calculated how black holes radiate, he found something extraordinary. The radiation isn't coming from inside the black hole. It's coming from just outside the horizon, where quantum effects create particle pairs. One particle falls in, the other escapes. That escaped particle is what we see as Hawking radiation. But here's the problem. Hawking's calculation shows this radiation is completely thermal. It's random. It carries no information about what fell in. It's like the difference between burning a book and getting meaningful smoke signals versus getting random ash. The radiation tells you nothing about the original information. So we have a paradox. General relativity says information falls in and hits the singularity. Quantum mechanics says information must be preserved. Hawking radiation seems to come out randomly, carrying no information. Something has to give. This is where your intuition is, about to betray you. You want me to tell you which theory is right and which is wrong. But that's not how nature works. Both theories are right in their domains. General relativity perfectly describes space-time on large scales. Every prediction it makes about orbits, gravitational waves, time dilation, all confirmed. Quantum mechanics perfectly describes the microscopic world. Every prediction about atoms, particles, forces, all confirmed to incredible precision. The problem isn't that one theory is wrong. The problem is that we're asking them to work together in a regime where neither was designed to operate. A black hole forces quantum mechanics to deal with curved space-time. It forces general relativity to deal with quantum uncertainty. They speak different languages. Let me give you a taste of how deep this goes. In quantum mechanics, empty space isn't empty. It's filled with virtual particles, constantly popping in and out of existence. These aren't metaphors. They're real enough to create measurable forces. Near a black hole's horizon, some of these virtual particle pairs get separated. One falls in, one escapes. That's Hawking radiation. But here's where it gets really weird. The escaping particle has to borrow energy to become real. Where does that energy come from? It comes from the black hole itself. The black hole gets lighter. It shrinks. It evaporates. Now think about what this means. A black hole that weighs as much as our sun would take longer than the age of the universe to evaporate. But a black hole, the mass of a mountain, would evaporate in less than a second, releasing the energy of millions of hydrogen bombs. The smaller the black hole, the faster it evaporates, the hotter it gets. This creates another puzzle. As the black hole evaporates, where does the information go? The early radiation comes out when the black hole is large and cold. This radiation is nearly thermal, random. It carries almost no information, but most of the mass and therefore most of the information comes out in the final burst when the black hole is tiny and hot. Is the information hiding in correlations we can't detect? Is it spread across the entire evaporation process in ways too subtle to measure? Or does it really disappear, only to be recreated in the final explosion? Some physicists propose that information never actually crosses the horizon. Maybe it gets stuck at the surface, encoded in the quantum structure of the horizon itself. From the outside, you would never see information cross the horizon. You'd see it get spread out and encoded on the surface like a hologram. But if that's true, what happens to the person who falls in? Do they experience hitting an information-encoded surface, or do they smoothly pass through into the interior? And if there's no interior, if everything is happening on the surface, what does that mean for our concept of space? Others suggest that the interior of a black hole might be connected to the exterior in ways we don't understand. Maybe information that falls in doesn't disappear. It gets entangled with the Hawking radiation coming out. The radiation looks random locally, but globally, it carries all the information in quantum correlations. This isn't just speculation. These ideas have mathematical teeth. When physicists calculate the entropy of a black hole, roughly, how much information it can store, they find it's proportional to the area of the horizon, not the volume of the interior. That's deeply strange. It's like saying the amount of data you can store in a computer depends on the size of the screen, not the size of the hard drive. At some point, you hit bedrock. We don't have a theory of quantum gravity. We don't know how to marry Einstein's smooth space-time with quantum mechanics' jittery uncertainty. The information paradox isn't a failure of physics, it's a signpost pointing toward new physics. But here's what we do know. The paradox has forced us to think more carefully about what information actually means. Information isn't a thing, it's a pattern. It's not about what something is made of, but how it's organized. Consider this. Every time you make a measurement in quantum mechanics, you create information. Every time particles interact, they exchange information. The universe isn't made of stuff. It's made of relationships, correlations, entanglements between different parts of reality. When you burn a book, you're not destroying the atoms that made up the paper and ink. You're rearranging them, changing their relationships, scrambling their organization. The information is still there. It's just become very hard to extract. But hard and impossible are different things. The black hole information paradox is asking whether the universe distinguishes between very hard and impossible. Is information conservation a strict law like energy conservation, or is it just a very strong tendency that can be violated under extreme circumstances? Some physicists think the solution lies in the holographic principle. Maybe all the information that falls into a black hole isn't really going inside. Maybe it's getting encoded on the surface, the event horizon, like a hologram. Three-dimensional information stored on a two-dimensional surface. Others think the solution involves the geometry of space-time itself. Maybe the interior of a black hole isn't what we think it is. Maybe the singularity is a mathematical artifact, and the real geometry is something we can't yet visualize. Still others propose that information does get destroyed, but only temporarily. Maybe when a black hole completely evaporates, the information gets released in the final burst of radiation, like a cosmic reset button. The truth is, we don't know yet. And that's not a failure. That's an opportunity. Here's where you need to flip your thinking. Stop asking what happens to information in a black hole. Start asking, what does the information paradox teach us about reality? First, it teaches us that our concepts of space and time might be emergent, not fundamental. Just like temperature emerges from the motion of atoms, maybe space-time emerges from something more basic, something we can't yet see. Let me make this concrete. When you measure the temperature of a gas, you're not measuring a property of individual atoms. Atoms don't have temperature. Temperature emerges from the collective motion of billions of atoms. It's a statistical property, meaningful only at large scales. What if space-time is the same? What if the smooth fabric of space and time that Einstein described is like temperature, an average, an approximation that emerges from something more fundamental, happening at a scale we can't directly observe? Some researchers think that fundamental scale might be networks of quantum entanglement, information connecting distant parts of the universe in ways that transcend our normal notions of locality. In this view, space-time isn't the stage on which physics happens. It's constructed from the quantum relationships between the actors. Second, it teaches us that information and gravity are connected in ways we never expected. The fact that black holes have entropy, that they have temperature and can evaporate, suggests that gravity isn't just geometry. It's intimately connected to quantum information. Here's a mind-bending possibility. Maybe gravity itself is an emergent property of quantum entanglement. Maybe when you entangle quantum systems, you create something that looks like curved space-time. Maybe Einstein's equations aren't fundamental laws. Maybe they're approximations that work when you have lots of entangled quantum information. This isn't just philosophy. Researchers have shown that you can derive Einstein's equations from assumptions about quantum entanglement and information theory. Gravity might not be fundamental. It might be emergent, like temperature or pressure. Third, it teaches us that the boundaries we draw inside versus outside, past versus future, might be more fluid than we thought. The horizon isn't just a point of no return. It's a place where our normal notions of causality break down. Consider this. If information never actually crosses the horizon, then what does it mean to say something is inside a black hole? If everything is encoded on the surface, then maybe the three-dimensional interior is an illusion. Maybe space itself has fewer dimensions than it appears to have. This is called the holographic principle, and it's not just speculation about black holes. Some versions suggest that our entire three-dimensional world might be a projection from a two-dimensional surface, like a hologram. The information describing everything in this room, every atom, every quantum state, might actually be encoded on a distant boundary surface. Most importantly, it teaches us that nature doesn't care what feels satisfying. We want clean answers. Information is conserved, or it isn't. Black holes are described by relativity or by quantum mechanics. Nature says it's more complicated than that. But here's the fascinating part. The information paradox has led us to one of the most important insights in modern physics, the holographic principle. If you take a sphere and ask how much information it can contain, your intuition says it should depend on the volume. Bigger sphere, more information. But black hole physics suggests it depends only on the surface area. This has profound implications. It suggests that the amount of information in any region of space is limited not by the volume of that region, but by the area of its boundary. It's as if the universe has a built-in compression algorithm. Take your room. According to the holographic principle, all the information needed to completely describe everything in your room, every atom's position and momentum, every quantum state, could in principle be encoded on the walls. The three-dimensional space inside would be a kind of projection, a useful illusion created by the information processing happening on the boundary. The real shift is this. Instead of treating the information paradox as a problem to solve, treat it as a lens through which to see deeper structure. The paradox isn't breaking physics. It's revealing physics we didn't know existed. This is the part your brain wants to reject. You're comfortable with the idea that physics has answers, clean, definite answers. But the most interesting parts of physics live in the gaps between theories, in the places where our current understanding breaks down. Think about what this means for our concept of reality. If space and time are emergent, if gravity is a collective effect of quantum entanglement, if three-dimensional space is a projection from a two-dimensional surface, then everything you think you know about the basic structure of reality needs to be reconsidered. But that's not a reason to despair. That's a reason to get excited. We're not just studying black holes. We're using black holes as laboratories to probe the deepest questions about the nature of reality itself. The information paradox isn't telling us that physics is broken. It's telling us that the universe is stranger and more subtle than we imagined. Information might be more fundamental than space and time. Gravity might be an emergent property of quantum entanglement. The inside of a black hole might not even exist in the way we think it does. Reality doesn't care what feels reasonable. If the mathematics demands that information be preserved, and if general relativity demands that it disappear, then our job isn't to pick sides. Our job is to find the deeper truth that makes both perspectives special cases of something more general. Now let me tell you about something remarkable happening right now. In 2020, Stephen Hawking won a bet he made decades earlier, posthumously. The bet was about whether information is preserved in black hole evaporation. Recent theoretical work suggests that information does come out, but in a very subtle way that Hawking couldn't have anticipated. The key insight involves something called quantum error correction. When you store data on a computer, you don't just write it once. You encode it in patterns that can survive corruption. If some bits get flipped, you can still recover the original information from what's left. The connection isn't just mathematical, it's conceptual. Both black holes and quantum computers are systems where quantum entanglement plays a crucial role in information processing. Both challenge our classical intuitions about how information flows through space and time. But the most exciting development is experimental. For the first time in history, we're actually detecting gravitational waves from black hole collisions. When two black holes spiral into each other and merge, they create ripples in space-time that we can now measure. These detections aren't just confirming Einstein's theory. They're giving us new ways to probe the information paradox. When black holes merge, what happens to the information they contain? Does it get preserved? Does it get scrambled? The gravitational waves might carry subtle signatures that could help answer these questions. We're also getting better at simulating black holes in the laboratory, using ultra-cold atoms or light in optical fibers. Researchers can create artificial event horizons that obey the same mathematical laws as real black holes. These analog systems might let us study Hawking radiation directly for the first time. What's emerging from all this work is a picture of black holes as fundamental laboratories for testing the deepest principles of physics. They're not just exotic objects in distant space. They're theoretical laboratories where quantum mechanics, general relativity, thermodynamics, and information theory all intersect in ways that push the boundaries of human knowledge. So what are black holes really? They're not cosmic vacuum cleaners. They're not mysterious monsters. They're laboratories. They're the places in the universe where our theories break down and new physics begins. The information paradox isn't a bug in our understanding. It's a feature. It's nature's way of telling us we're asking the wrong questions. We're not supposed to understand black holes with our current theories. We're supposed to let them teach us new theories. Every time you hear about black holes swallowing information, remember this: the universe doesn't swallow anything. It transforms it, it encrypts it, it stores it in ways we're just beginning to understand. The information paradox isn't about what we don't know. It's about what we're about to discover. The universe is under no obligation to make sense to you, but it is obligated to be consistent with itself. And that consistency, that hidden logic operating behind the paradox, that's what we're really hunting for. Black holes aren't destroying information. They're teaching us what information actually is. They're showing us that space and time and matter and energy are just different facets of something deeper, something that doesn't have a name yet because we haven't been smart enough to see it clearly. But we're getting there, one paradox at a time, one broken theory at a time, one impossible question at a time. Understanding isn't comfort, it's power. And right now, black holes are showing us just how much power we still have left to discover.